Math 30-2, so we're going to continue on with probability here. We are going to talk about conditional probability today. But before we do that, we're just going to review a little bit about mutual exclusivity here. So Sally's been asked to draw a card from random. She draws a face card or a red card. He wins a point. Okay, seems pretty good. So let's draw a Venn diagram that represent the two different cards that he can get here. So let's just do that. Hopefully you have already tried this question. If you haven't, give it a good pause. So you're going to draw a Venn diagram that represents face cards. That's one thing you can draw. And red cards, because that's another kind of card that you can draw. Give this video a pause. Try that out. Answer the questions down below. And I'll see you in a bit. All right, so hopefully you paused and tried that. Sally's about to draw a card. So we're going to draw a Venn diagram. So just want to see, are these two pieces, are they mutually exclusive? Do they have anything in common, which means they're non-mutually exclusive, or they have nothing in common? Would there be an empty set in the intersection between the two? So I look at this here and I think, okay, what do we have here? So we could have a red face card, right? Kind of makes sense. There are 12 face cards in total. Half of them are going to be red, right? That's my guess. If we look at red cards, we got hearts and we got diamonds. Black cards that we have clubs and we have spades, right? So we have those cards. In each one, we have a queen, a king, and a jack for each one of these, right? So those are your face cards, king, queen, and jack. Kind of weird order I put those in. So if I have 2 red suits and 3 face cards each, that means I have 6 cards that are either face cards and red cards at the same time, which leaves me on the red side here. How many red cards do we actually have? And how many face cards do we actually have? Okay. So what we know is there are 52 cards in the deck, right? How many face cards are there? So I just quickly punch in my calculator here to figure that out. Oh, actually I don't have to. It's 3 times 4. So I know there's 12 face cards altogether. I'll put a little 12 in here, which means these two pieces, this piece here and this piece here, I have to add to 12. Red cards, half the deck is red. So if half the deck is red, what do we have there? 26, which means there are 26 more red cards that are not face cards. Okay? So are they mutually exclusive? No. There are 6 cards in common. What's the probability of drawing a face card or a red card? Okay. So to figure out the probability of drawing a face card or a red card, so that's the union, I'm looking at this calculation here. So I got a face card or a red card. So if remember from the previous lessons that we have here, to find probability, you just have to know the number of the favorable outcomes and divide it by the number in this sample space, in this case, the universal set. So I know there's 52 cards there, okay? Now the number in the set up here, so I could just add these boxes up here. So I got 6 of those, plus 6 of those, plus 20. And I could just do it that way. And I would get 32. 6 plus 6 plus 20. 32. Okay. 52. Or, I'll simplify this down in a bit. I could do it the other way, the other formula, where we have the 2 circles. So we have 12 in one circle, plus the 26 in the other circle. And then I'm going to minus out the 6 that's in between. So the formula from previous class, where we said that this thing with the union of these two is the number in one set plus the number in another set minus what they have in common, the intersection between the two. So I can use that formula as well. If you look at this very carefully, it's the exact same. You end up with 32 over 52. And 32 over 52 reduced down is 8 over 13. Okay, so there's the probability that you're going to draw one of those two. Okay, that's just a review from the last class, but now we're going to be talking about conditional probability. Before we talk about conditional probability, we need a few new definitions. There's a lot of definitions in this one. Maybe I'll create a sheet of all the words that we have and all the different definitions and maybe some formulas. We do have a formula sheet here. I was looking at it. Look at the formula sheet here. There are things about probability on the formula sheet that exactly what this formula is. So they are there. It's just I'll have to get that to you. And this formula, I believe, is on the formula sheet too. Yeah, it is. This one down here is also on the formula sheet. Okay. So if the probability of one event, so imagine you were going to do this one above here, and I said, okay, I'm going to draw a face card, and then I'm going to draw a red card. So I'm drawing two cards. The probability of one event depends on what happens to the first one. Did I draw a red card? Did I not draw a red card? So when I do that, also when I draw a card out, my sample space is decreased, so my probabilities have decreased. And when a probability of one event depends on another event, we call this dependent events. So by doing one event, it changes the probability of something else. You can see this little example down here. You can draw a heart from a card, and then you draw another heart from the same deck, but you didn't replace it. You didn't put the other card back in there, so the new probability is going to be slightly different rather than, say, divided by 52, because I have one less card, I'm going to divide by 51. All right, so this is what we call conditional probability, where the event of B changes because of what A did, right? So we call that this. So if I want to calculate the probability of B, if I know that A has happened or A is going to happen, right, or A is going to change this B, that's what the symbol means. The probability of B if A occurred has already occurred, right? So when we're doing some calculations up here, if I want to know if one thing happens to the other, so if I do like the probability of A and B happening at the same time, so if you're drawing two cards, you do the probability of one, then you find the probability of the next one as if A has already occurred and you multiply those two together. So the very important formula. Right? Now the word and, remember, can be also written as the intersection here. Okay. So you might see this symbol instead. It just means they're happening at the exact same time. Okay. Again, we're going to use some tree diagrams here to kind of make these questions a little bit easier to understand and look at. So like this next question here, we're going to use a tree diagram to solve this one, to see how it works. And I'm going to talk about how you can verify to see if you did something correctly. Okay, so a jam manufacturer knows that the box of 48 jars, 5 of them will contain less jam than shown on the label. Okay. Determine the probability that if you just draw 2 jars out at random, that they'll contain less jam. And when you think about this, you always think about, rather than just going in and grabbing 2 at one time, just grab one and then grab another, right? So just think of this, and I'm going to just draw it as a tree, okay? So I'm going to reach in, I'm going to grab my first jar, okay? And there's 2 outcomes for the first jar. The first jar could either have less jam or it can have enough jam, right? So those are my 2 different options for this jar. Now, the probability of it having less jam at this point, because this is the first jar, is how many favorable outcomes of this one. There'd be 5 that have less, and in the sample space, there's 48 jars. So it's 5 out of 48. That's my probability of getting less here. Now, the probability of getting just enough is just the other side. So if 5 jars have less, then 43 jars out of the 48 should have enough. So those are the two different probabilities. Okay, so let's just say on the top. So you picked out the less jar. So now you have a less jar coming out. I'm going to reach in and get my second jar. Now that second jar has two possibilities too. It has less or enough. Right? Now the problem is that it's not going to be, for the second jar, it's not going to be 5 out of 48. I've already pulled out one of the less jars. So there's only, to have another less jar come out, there's only 4 of them left inside the container. And because I pulled a jar out, it's not out of 48 anymore, it's only out of 47. So of the 47 jars that are left, only 4 of them have less. And then I can see on the other side here, 53, 47, or 43, sorry, 47. There's the other jars. That number hasn't changed. You notice there's 43 down here, is 43 up here. Because I pulled a less jar out, I didn't pull enough jar out, so there's still 43 of them in there, but there's one less jar in total. And the same thing happens down here. For the second jar, if I pulled out one that had enough already, so I put that aside, the probability that me getting something that has less, because I pulled out enough, there's still 5 jars that don't have enough in there, and there's 47 of them. And then if I look here, I got enough. Okay. Now this one here, I pulled out enough. So I took out one of those enough ones and it just has enough. I put it on the side. That means there's one less. So I'm going to have a 42 here. And then on the bottom, I still have 47. Okay, so these are all the probabilities. Now the probability of getting 2 less, determine the probability that jars at random will contain, the 2 at random will contain less jam, is up here. Now, if you go back to the formula that's up there, the probability of these two things happening at the same time, probably these two things happening at the same time here, is just the multiplication of the two probabilities. The probability of it happening and then the probability of the other guy happening if the other one has already happened. You can see that that's what we calculated. This is the probability of it happening. And the second probability here is the probability that's changed because the first one happened already. So I'm going to multiply those two together, and I'm going to get 20 over 48 times 47. Oops, 48 times 47. 20 over 2,256. Okay. We can reduce that down. We're going to talk about this in a second. Now, that's the probability. Actually, I'll just reduce it down right now. Do you want it in decimal form? No, doesn't say anything about that. So this reduces down to 5 over 564. So that's the answer we're looking for. 2 less jars, that's the probability. Now, to verify we did this tree correctly, I'm going to find the rest of these probabilities, just to verify. We found the answer up here, so we're good. This is the answer. This is the probability we get 2 less jars. It's a really small percentage, like less than 1%. Now, to find these other probabilities, I'm just going to multiply these two together. And I'm going to get a bunch of different probabilities here. Just a second. Okay, so this one here turns out to be 215 over 2256. Now you're going to see why I'm doing this in a second. Sorry, 47, 43, 48. So I'm just going to multiply these two probabilities together. This probability just ends up being the same. And this last one here is going to be a pretty big probability, actually. It's most likely that you're going to pull 2 jars that have enough out. Divided by 226. What we get here is 301 over 3. So it's a pretty high probability that's going to happen. Now, the reason I did this is just so what happens if I add these together? What if I add all of these probabilities on this side over here? What if I add those together? What do I get? Well, if I go this plus this plus this plus this, and I add them all together, punch in my calculator, what I get is 1, exactly 1. So this is a certain event, right? So that means that one of these things has to happen. Either I pull 2 less jars out, or less than enough, or nothing less, or 2 enoughs. Those are the only outcomes I have. So this number has to add up to 1. So that's just a verification to see, did I make this tree correct? Did I go through the math and I do it all? So if I were to add all of these pieces together, I should get 1 at the end. So it's a certain event. Something's got to happen, one of those 2 things, or one of those 4 things there has to happen. Okay. So you can see that by doing the first jar, it's changed the second jar's probability. So the probabilities on this side over here change the probabilities on this one. So let's think about this next one and see, is that the case for this one here? So Tony draws a card, well shuffled deck. He draws another card from the deck without replacing it. So that's a very key word, without replacing it. Because if I don't replace it, I've changed the sample size. Therefore, the events are dependent on each other. So these are dependent since the sample size has changed because I didn't replace the card. Also because in the next question, I want to take both cards being jack, I've also changed the size of the favorable outcomes. Now, see, we don't have to do the tree, the whole tree. We only have to do part of the tree. So if I want to figure out the probability that I pull a jack and another jack, I'm just going to take, what's the probability of pulling a jack, one of the jacks out? I'm going to times it by the probability of pulling another jack when I pulled a jack out already. So those are my 2 things I'm going to multiply together. That's exactly what we did at the very top there. For this line, we took the probability of taking one of the jars out and then times it by the probability of taking another jar out. If I've already taken another jar, you can see that 4 has changed, the 47 is, or the 5 is changed to a 4, and the 48 is changed to a 47. So down here, we're going to do the same thing. So there are 4 jacks in a deck of the 52. So that's the probability of pulling a jack out, 4 to 52. Now, because I pulled a jack out, there's 1 less jack, and now there's only 51 cards left in the deck. So that's the probability of pulling another jack out. So I'm going to multiply those 2 together. You get a probability of 1 over 221. So the 1 in 221 chance, so you're going to pull 2 jacks out of the deck. There you go. Okay, it's pretty easy. If you don't draw a tree, you don't have to. Let's look at this next one. Connie spins a spinner. Equals sections 1 to 8. She then rolls a dice. The spinner lands on a 3, and the sum is 2 of the 2 numbers is greater than 6 of the. Yeah. Just one second. Okay, so she's going to spin the spinner. It's going to land on a 3. If she adds the 3 with the dice, and it ends up being greater than 6, Connie will win a point. Are they dependent on each other? Yeah, they're dependent on each other. Okay. I can only get a point if there's a 3 on the spinner and they add up to this. If there's a 3 doesn't land on a 3, then I don't get a point. So yes, they are dependent on each other. And I'm not going to bother writing. Maybe it's you need a 3 to score. Okay, so let's determine the probability that she's going to actually win this point. So the probability that she rolls or spins a 3, so let's call that a spin 3, and she has a sum that's greater than 6, is going to be the probability of her spinning a 3 times the probability, that she doesn't spin a 3. Probability that the sum is greater than 6 if she spun a 3 already. So that's the condition here. So that's the event. So the spin of 3 is pretty easy. There's 1 out of 8 chances. So there's number 1 to 8. I want to spin a 3 and only a 3. So there's a 1 in 8 chance that she's going to spin a 3. Okay? Now, once she's spun a 3, my sample space has changed. Okay? So my sample space, I've spun a 3, and I have an 8-sided dice. 1, 2, 3, 4, 5, 6, 7, 8. Now, if I add these together, because I want the sum to be greater than that, so if I had the spinner of 3, and this is my dice up here, I'm going to add these together and get this new sample space. Now, you notice in our sample space, that these numbers here are the numbers that are greater than 7. There's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 things in my sample space, and 1, 2, 3, 4, 5 of them are winning. So there's going to be a 5 out of 8 chance that she's going to win that. So if she spun a 3, this would be 5 times 1, so I got 5 on the top, and then 8 times 8. So she has a 5 out of 64 chance that she's going to win a point. Not very good chances, but that's what's going to happen here. Okay? So you can see what happened there. So she spun a 3, and then my sample space has changed accordingly to this new sample space down here, and then I have a new number of outcomes as well. My sample space could be rather large if you look at just the total sample space to start off with. I have 1 to 8 down here. Oh, what was I thinking? I got a standard dice on this one, so I got to change this. It only goes up to 6. My bad. Sorry about that. I'm not going to bother rewriting the video on this one. I'm just going to change that. You can see that it's only 3 this time, not 5. That's my bad. I'm sorry about that. So you're going to change this to a 3, and this is going to be a 3 now. So it's actually 3 out of 64, and I probably should reduce it down if I can. No, can't reduce it down, so my answer is just going to be 3 out of 64. And there you go. So by doing one thing, it's changed the sample space of this one. Okay, so I'm just going to stop the video at this point. What I want you to do is look at this next page, try them out, come back, and I'll go over them in the next video. All right, see you then. Bye.